Alright, so last time we started looking at random line. We started looking at filtrations on standard groups. Namely, we kind of had this idea of on ultrametric space, the idea that we can use the valuation as like a map to define filtrations. I forget what that kind of map is called, but that was a thing we saw before. So, just a reminder, we have W be our valuation, we have G lambda be the elements of G, of our group G. So valuation is at least lambda, plus making that inequality strict. Yeah, you can go back and watch the old video if you want. So, now, to start off this video, we have a theorem. We're going to let A and B be ideals of our valuation ring such that A is contained within B, contained within A squared. Then the reduction map phi B sending G to G with A reduced by B induces an isomorphism of GA over GB, which is elements of a group whose indices are in A and B respectively, onto the additive group of A over B to the N. And our proof is pretty straightforward. We saw that f of x and y is congruent to x plus y mod a squared for, of course, x and y being in GA. From this and our first theorem, which essentially just gave us that for x, y, and g, if they're congruent mod A, their components are congruent mod that generating ideal. And so that'll give us this theorem. And it comes with a corollary. So we're going to let lambda be a weight of something in our maximal ideal and be not infinity. Then G lambda over G lambda plus, so essentially that just guarantees this is not trivial, is isomorphic to the additive group of our valuation ring over our maximal ideal to the N as an additive group, of course. I think I already said that. So from that, so when you prove that, So by definition, we can choose some A and M in our maximal ideals with a valuation of lambda. And we can pick I'm going to call it a hat. They call it A, confusingly, of course, B generated by A. Then, by our above theorem, G A hat over G A hat plus is isomorphic to A hat over A hat M to the N. And then we just need to note that the map from alpha to alpha times A defines an isomorphism of A over M onto A hat over A hat M, and that gives us our corollary. There's a second corollary following this one. So we suppose our base field is locally compact. And that P is the character of the evaluation ring modded the maximal ideal. Then we have a few consequences. First off, G over lambda over G over lambda plus is a commutative, finite P group for lambda being in the image of the maximal ideal under M and not including infinity, of course. We also have, secondly, that G lambda over G lambda plus is a P group for all lambda being the valuation, using the non-trivial valuation of an element in our base, in our maximal ideal. Finally, G is a projective limit of P groups. And the proof of this, I have to scan through it first. As K is locally compact, first off, E over M is compact and discrete. So finite. Secondly, M is compact. So evaluation takes on a minimal value on some elements, say A and M. Then from this, our maximal ideal is generated by A. So A is a discrete valuation ring. We then have our first statement from above, from our first topic and our first corollary, of course. And then this, along with statement 2, gives us our second statement. And our second implies the third. It says, and now we're going to use our filtration of G to study the power maps. The setup, we're going to let K bar be our A over M, which is also going to be, which we note is the residue field of K. And we're going to let, they just don't have symbol there. I'm sure from context it's P. It's going to be the characteristic of the residue field. Suppose that R is relatively prime to P. Then for all lambda in the evaluation map of M, not infinity, the rth power map FR defines an analytic manifold isomorphism of G lambda onto, they have it here as G lambda onto itself. That might not be right, we'll check when we get there. So, look at our proof. So we know the image of R in a residue field is a unit. In K, so R is a unit in A. Hence, FR is an invertible formal power series in this. Then theta, which we define to be the inverse of our power map, is absolutely convergent on G, and the image of FR on theta, of course, FR on theta and theta on FR is identity by our previous lemma. Since FR and theta preserve G lambda Fr is a bijection on G lambda. Finally, we know that the derivative of Fr at each x and g is congruent to r times r to r times identity mod the maximal ideal, and hence is invertible. Thus f sub r is a tau, and hence an analytic isomorphism. Okay, and yeah, we're just gonna keep working through a few more of these consequences here. So suppose now the characteristic of our base field is 0 and the characteristic of its residue field is non-zero. Is P supposed to be that, or I think P might just be some element. We're setting mu to be the evaluation of P. Then for lambda in the value, lambda being a valuation of M, with it being in between lambda over P minus 1 and infinity, Fp is an analytic isomorphism of G lambda onto G lambda plus mu. Alright, let's look at the proof of this. Well, by Lazard's theorem, Fp of some x is P x plus Vx plus Cx, where the order of phi is at least 2, and the order of C is at least P. Then for x in our x energy lambda and alpha, whose absolute value is at least 1, the evaluation of x v alpha has to be at least lambda times the size of alpha. Which we can then further expand into the evaluation of phi of x being at least lambda, and the evaluation of c of x having to be at least p lambda, which is lambda plus p minus 1 lambda, which is at least lambda plus v. From this, we have that fp of g lambda is contained within g of lambda plus mu. To show that fp is an analytic of g lambda onto g lambda plus mu, we're going to choose A and G with a valuation of lambda, and we're going to consider a function f from a to the n to a to the n as f of x being 1 over a times p times fp of ax. Then from this we get that f of x is equal to x plus 1 over alpha times our phi of ax plus 1 over ap of c times a of x, of a times x. So now we're going to let r be a real number between 0 and 1, such that both the absolute value of a and the absolute value of a to the p minus 1 over the absolute value of p are less than r to the p minus 1. From this, first off, the coefficients of degree, say I being at least 2, in this 1 over alpha, 1 over a times phi of ax, have an absolute value less than or equal to, of course, the size of a to the I minus 1, which is within our r to the I minus 1. And secondly, the coefficients of degree at least p in our 1 over ap times c of ax have absolute value or a new line here just in case, less than or equal to a to the I minus p times a to the p minus 1 over the size of p, which is less than or equal to r to I minus 1. And when we get to the appendix, you will see that these imply f and its formal inverse theta converge absolutely on a to the n. Being able to actually compose f and theta on a to the n, showing that f is an analytic isomorphism of a to the n onto a to the n, which will make fp from g lambda to g lambda plus mu an analytic isomorphism. Alright, and from this we have a theorem. Let G be a Lie group over K. Then there exists U, which is going to be an open subgroup which contains no finite subgroup H, sorry, I'm occupied, such that the size of H is relatively prime to the characteristic of our base field. This is automatic because G has a standard open subgroup. We can just work with that. And so we can just move on to our appendix. If I can figure out how this is ordered. Yeah. Alright. So our first topic in the appendix here is going to be maximal compact subgroups of the general linear Lie group in n dimensions over K. So we're going to have K be a locally compact ultrametric field with a valuation ring A, which itself has a maximal ideal A, and we're going to let G be the general linear Lie group over A in some dimension n, which is not specified. We start out, we have a lemma where L be an A submodule of K to the n. Then the following are equivalent. First off, L is finitely generated over A, and L generates K to the n over K. Secondly, L is free of rank n over A. And of course 2 implies 1, so since the evaluation ring is of course going to be a principal ideal domain, L is free, and the A rank of L is n, as L generates k to the n over A actually. And we call such an L is called a lattice in k to the n. Alright, another lemma. So we're going to take a sequence of R lattices in k to the n, and let L be the A submodule of k to the n generated by these Li. Then L is a lattice. Don't know why I capitalized lattice like that. And we're going to go for criteria 1 here. So L clearly generates k to the n over k as each Li does. And of course, since Li is finitely generated, over A, so is L. And this brings us to another lemma. Lots of lemmas here. So we're going to let L be a lattice in k to the n. And we're going to let k sub L be the subgroup of the n-dimensional general linear Lie group over k, which send L onto L. Then for some alpha in GLN of k, this KL is just the conjugate of our G by this alpha. So k to the L is compact and open. So if we call by our definition by our theorem defining a lemma, lattice, it has to be free of rank n over A. So we can choose alpha in GLNK such that the image of A to the n under alpha is L. Then as G is just GLN of A by definition, K is just alpha G alpha minus 1. And yeah, now we can move on to another lemma. And it's going to be our last lemma, then we've got 2 theorems, and then I think we can call it. So we're going to let L and L prime be lattices in K to the N with the subgroup of preserving L being inside the subgroup preserving L prime. And there exists L in K to the alpha such that L prime being lambda times L and K to the L is actually going to be equal to K to the L prime. So we can scale L prime by lambda in K to the whatever. From that we can suppose L prime is an L, but not in L times our maximal ideal evaluation ring. Now we're going to let V be L over ML and V prime be L prime plus M of L over M of L, which is going to be a non-zero vector subspace of V over the residue field A over M. Since K to the L is inside K to the L prime, the lattice L prime is invariant by K to the L. So its image V prime in V is invariant by K to sub L, which is the same thing saying it's by GL of V. Since V prime is non-zero, it must be V. So L prime plus ML is L, and by, it just says a standard argument quoted as Nakayama's lemma, L prime being L. And there's a couple theorems to follow this up, and then we are done for this video. Let H be a compact subgroup of the n-dimensional general linear Lie group over K. Then, well, first off, there exists a lattice M in K to the N such that H sends M onto M. And secondly, there exists an alpha in GLN of K such that H is contained in the conjugate of G by alpha. And the proof. One obviously implies two, so we just need to improve part one. So we just need to choose a lattice L and K to the N. For example, we can pick L to be A to the N. Then H sub L is going to be H intersecting KL, which is the subgroup of H sending L onto L. Since KL is open in GLN of K, HL is then open in H. So HL has finite index in H. Since H over HL is compact, and discrete, and so is going to be finite. Let M be the A submodule generated by sigma L for sigma in H. Then H sends M onto M. And from previous lemma, M is a lattice. Another quick theorem, and then we will be done. 3 parts, but the first implies the other two, so it's only really about the first one. First off, G is, as promised, a maximal compact subgroup of the n-dimensional general linear Lie group over K, which gives us the maximal compact subgroups of G, L, and K are the conjugates of G. And thirdly, every maximal compact subgroup of every, it's not, they don't have to be maximal, but every compact subgroup of GL and K is contained in a maximal compact subgroup of GL and K. And the proof, of course, as I said, we're just going to prove part 1 with 2 and 3 being immediate consequences. Suppose G is contained in a compact subgroup H of GLN of K. Then, by our first theorem in this section, there exists a lattice M such that H is in K of M. So G must be in K of M. So by our fourth lemma, G is K of M. Thus G is maximal. Alright, and next up, we're going to look at some convergence lemmas, maybe some applications of filtrations on standard groups, and then we'll be switching over to Bourbaki. So we'll be kind of recovering some of this to some extent, but that's kind of how it goes sometimes. Thanks for watching.